So at the end of this video lecture series, students will be able to identify and use the correct gas law in various gas law problems. And students will be able to convert their units into Kelvin so that they can do the appropriate calculations with the above gas laws.
The gas laws allow us to interrelate a specific number of moles of a gas and analyze it with respect to changing specific parameters within a container or within a specific situation. So what do I mean by that? Well, the fact that we have a constant amount of the gas allows us to look at how a pressure or a volume or a temperature change will alter other variables within the specific gas law. And so the combined gas law interrelates pressure, volume, and temperature. So P1, V1, T1 represent the amount of gas at a specific pressure, volume, and temperature. P2, T2, and V2 represent a new set of conditions in which we can compare to the original set. So in this specific situation, if we have 5 of the 6 variables, we can manipulate the equation, isolate that variable, and subsequently see how that variable is going to change based on a new pressure or temperature or a new pressure and volume. And basically we'll look at those details in a little bit. But the neat thing about the combined gas law is that you can get the other gas laws from this original combined gas law equation. Okay, so if you are at constant temperature, meaning that your temperature doesn't change, all you do is cross out your T1 and your T2, and you end up with P1V1 equals P2V2. If you're at constant pressure, you just cancel out your P1 and P2, and that gives you V1 over T1 equals V2 over T2. And then, of course, at constant volume, you can just cancel out the volumes, and you end up with the P1 over T1 equals P2 over T2. So all of these equations can be utilized in order to solve for basically the variable that's being observed. So, you know, your volume or your temperature, your pressure. And depending on what you're given in the question, that's going to dictate the equation that you use. So we'll go ahead and look at that in a little bit more detail here soon.
So let's go ahead and let's work on a practice problem. So a sample of gas occupies 2 liters at 0.90 atm when the temperature is 22.5 degrees C. What will be its volume at STP? Okay, so in this context, what I always do with these problems is first write out all of our variables. Okay, so volume 1 is going to be equal to 2.0 liters. Pressure 1 is equal to 0.90 atm. Okay, and my temperature, okay, is equal to 22.5 degrees C. So what I want you guys to notice here is that I've labeled each of these V1, P1, and T1 because that's the first set of data that I'm provided. The second set of data that I'm provided is the fact that everything's at STP. So remember, we're supposed to know what STP is. Okay, so standard temperature and pressure. So my temperature 2 is going to be 0.00 degrees C. My pressure 2 is going to be 00 atm. Okay, and of course my volume 2 is what they're trying to get us to solve for. Okay, so we know that we have 2 pressures, 2 volumes, 2 temperatures, so we know we're going to be using the combined gas law in order to solve for our V2. So now we need to get V2 all by itself, okay, and that is going to be accomplished by manipulating the equation, okay, and then P2, T1. Okay, now this is what we are going to be plugging our variables into, and so before we do that though, we want to make sure that we are matching up our variables in the appropriate manner. So remember, our units here for pressure have to match, okay, and our temperatures need to be in Kelvin. So we need to make some conversions here. So we're going to go ahead and add 273.15 to each of our temperatures. Okay, and that's going to give us our temperatures in Kelvin. Okay, and then we can go ahead and plug in our values. Okay, so this is now going to be what our equation looks like once we've plugged in all of our variables, and that's going to give us 1.66, okay, as our answer. Okay, units wise, Kelvin and Kelvin cancel. ATM and ATM cancel, and liters are left over. Okay, and the last thing we need to consider is significant figures. So this is going to be 2 sig figs. So 1.7 liters, okay, is what our final answer is going to be for our volume after we change the conditions. So Boyle's law basically interrelates pressure and volume, okay, and what we see with Boyle's law is that there's an inverse relationship between pressure and volume, okay. So if we look here, as volume increases, our pressure is going to decrease, and basically what we need to understand is that at constant temperature and with a constant quantity of gas, we can utilize this relationship here to figure out how the volume or how the pressure of the system is going to change. So this is how we're going to be using Boyle's law in the future.
If we go ahead and...
So here we've been given another practice problem. In this context, we've been told that we have a sample of gas that occupies a volume of 946 milliliters, okay, at a pressure of 726 millimeters of mercury. Okay, and they want us to know, or want us to figure out what the pressure is of the gas in a new set of conditions, which is going to correspond to a reduction in volume to 154 milliliters. Okay, and so they've told us that this occurs at constant temperature. Okay, so we know that we can ignore temperature in terms of our equation. So in this case, P1V1 equals P2V2 is the equation that we're going to be using. Okay, and we're going to be solving for P2. So P1 over V1 over V2 is going to be the equation that we plug our variables into. So before we do that, we want to make sure that our variables match up. Okay, we've got milliliters and milliliters. Okay, millimeters of mercury are going to be our pressure units, so we can go ahead and plug in our values. So when we go ahead and we plug this in to our equation, we get the following. So we're going to get 459, okay. So we're going to go ahead and look at our significant figures here. It looks like 3 sig figs across the board. Okay, so 4460. Okay, units wise, milliliters and milliliters cancel. Millimeters of mercury are left over. Okay, and this is our final answer in millimeters of mercury. We're going to go ahead and look at Charles's and Guy-Lussac's laws. With both of these laws, what we need to understand is that temperature is going to be directly proportional to either volume, okay, or pressure. Now, when we have a gas in a container, we're either going to have it in a flexible container or a rigid container. So in the context of the flexible container, we're going to be using Charles's law. And basically, what I mean by a flexible container is that the container can expand or contract. And basically that allows the pressure inside the container to be held constant while volume changes and temperature changes are occurring. In that same thought process, a rigid container is going to be where we see Guy-Lussac's law being applied. And the reason why that's the case is because in a rigid container, the volume is held constant, and you subsequently end up with pressure changes inside the container. Okay? So again, when you are doing Charles's and Guy-Lussac's law calculations, you want to make sure that your temperature is in Kelvin and that you are able to make that conversion and use it readily. So this next problem has told us that we have a sample of carbon monoxide that occupies a volume of 3.20 liters at a temperature of 125 degrees C. Okay, and we want to know the temperature at which the gas will occupy a volume of 1.54 liters. Okay, now they've told us we're at constant pressure, and so since that remains constant, we know that we're going to be using this equation. Okay, and we want to solve for T2, so we're going to manipulate this. Now that we've manipulated it, we're going to go ahead and check our variables and make sure we're plugging everything in correctly. So of course we check our volumes, we make sure they match, the units of liters and liters match, and we need to make sure our temperature is in Kelvin. Okay, so since it's not, we're going to add 273.15 to this value, and that's going to give us 398.15 Kelvin. Okay, and we're going to go ahead and plug this in now. So now that we've plugged all these in, we're going to go ahead and get our answer, which is as follows. Okay, and then we're going to check our significant figures. Okay, so it looks like we have 3 across the board, so this is going to be 192. And then units-wise, liters and liters cancel, Kelvin is left over, and so the temperature at which we will obtain the 1.54 liters is going to correspond to 192 Kelvin. So the last problem we're going to be looking at here, they told us we have a car tire that has a pressure of 1.88 atm, okay, and a temperature 25 degrees C, okay, and they want to know what the pressure in the tire will be, okay, at a new temperature, which is 37 degrees C. Okay, and so what we're going to go ahead and do, we're going to utilize this equation because they've mentioned nothing about volume, so what we're going to assume is that the volume is constant. All right, so P1 over T1 equals P2 over T2. Okay, and we're going to go ahead and manipulate for the P2 variable. And now that we've done that, we're going to go ahead and check our units and make sure we can plug them in. So if we look really quickly here, Celsius and Celsius are not what we want to be in. We want to be in Kelvin because it's a gas law problem. So we're going to go ahead and add 273 to each of these. And that will give us our new temperature values, which are as follows. So now we're going to go ahead and plug in our variables. And if we plug this into our calculator, we get the following answer. Okay, significant figure-wise, we're going to end up with 3. Okay, so we're going to end up with 1.96. And then units-wise, Kelvin and Kelvin are going to cancel, and we end up with our units in ATM.